what we want to review today for chapter 7. Next class, we'll have the exam over chapter 7. It's only one chapter, so that's the good news. I said, it's not so much material, but it's some of the hardest material. So make sure you get started early with the problems. Be able to do everything like the practice exam. Most of the problems will be like that. There could be some that are similar to homework that aren't on this practice exam, though. There are a few of those I might throw at you, but they'll be mostly similar to the review. So come by and see me. I have my office hour later today down the hall. It's in person unless you arrange otherwise. It's the same as the other exams. You need a calculator. Any questions on the exam?
2
Okay.
on the, oh, sorry.
Review sheet. Okay,
Yeah, my bad.
You go ahead and look at those then. Yeah. Nice. One of these, how about? Each one. Yeah, that's questions off of there. We'll get number 1 first. This is actually a very simple problem. If you get something on the exam, I'll try and keep this pretty straightforward. Try and put similar problems in similar order, but there may be some from the homework that are not on here, not very many. But I want to make sure you can do all the homework. Suppose I asked you this, cosine 105 degrees plus cosine 15 degrees is equal to what? Using cosine A plus cosine B equals 2 cosine the average of A and B times the cosine difference of A and B over 2. This was the sum to product formula that we did. 2 tuning forks, we could get a sound that went on and off. So the sum to product identity, you don't have to memorize those. You have to memorize all the other identities except for these sum to product identities. And I'll give you these, just like this problem. So how do I evaluate this? Exactly. Using this identity.
Plug cosine into, like, establish cosine 105. And just plug it in from here.
Yeah, just call that A and that B. I'm not, well, this first one, if I give it to you, it's really easy. Just call that A and that B and put it in. Right. So it's twice cosine A plus B over 2. Cosine A minus B over 2. You just put 105 plus 15 over 2. 105 minus 15. So that's it, A plus B over 2. All you're doing is putting, this is A and this is B into the formula. Because now this comes out to be cosine of 120 over 2 or cosine 60 degrees. This comes out to be cosine of 90 over 2, which is cosine of 45 degrees. Those are both special angles, right? I can evaluate those using the 2 triangles you absolutely have to memorize for this exam and all the other exams. All right, the 30, 60, 90 triangle has sides 1/2, square root of 3 over 2 and 1. Or if you like 1, square root of 3 and 2 if you prefer that. Twice as big as this one. And then there's this one, square root of 2 over 2 on each leg. One of the hypotenuse for a 45, 45, 90 triangle. So cosine of 60, let's see, is adjacent over hypotenuse, is 1/2. Cosine of 45 is adjacent over hypotenuse, is square root of 2 over 2. The 2 and 1/2 cancel each other. Easy as that. How about that for number 1? Then we said find the exact value of tangent minus 75 degrees. Right? There's at least 2 different ways to do this. What are the 2 ways that you think of maybe, or maybe you can think of more?
Well, the identity.
Yeah, and all identities. Well, which ones?
Like the numbers. I did negative 3.
Okay, so you did a sum identity. So the sum and difference identities is one way. If you can write this as a sum or difference of special angles, and you know you can, because you can do that for any multiple of 15 degrees, right? Any multiple of 15 degrees, use the sum or difference identity. Or, since it's half of a special angle, you use a half angle identity. I don't care which one you use, I didn't specify on here, right? Let's try what she said and use the sum identity. You can use minus 45, minus 30. I like to do this, and so you don't have to do this. But just to point out that you can, and sometimes it makes your day a little easier. Pull the minus out. Tangent is an odd function, so tangent of minus 75 is minus tangent 75, right? An odd function has the property that f of minus x is minus f of x. That's the definition of odd function, right? You can pull the minus out. We said tangent's odd, pull the minus out. Now I don't have to deal with negative angles. All right, and if you want, leave it in, right? This is minus 45 plus minus 30. I'd prefer to write minus the tangent of plus 45 plus 30, right? If you write any angle as a sum or difference of special angles, you can use the sum or difference formulas to evaluate it, right? Exactly. Provided these are special angles, don't write it as 60 plus 15. 15 is a special angle, you have to do this again, right? So I've got minus. Now the tangent of the sum, remember, is tangent plus tangent over 1 minus tangent tangent. So you have to memorize all these identities except for the sum of product and product of sum identities. It's a bunch, I know, but you actually need them in later classes quite a lot. There's tangent less than some of them, but the sine and cosine identities are everywhere in calculus and other higher level courses. All right, tangent plus tangent, or you put the angles in order, 45, 30, 45, 30. Now I've got these triangles memorized, so I can just calculate. Tangent 45 is opposite over adjacent. This over itself is 1. But then for tangent 45 here and here. Right? Then tangent of 30, I'll go up here. Here's 30 degrees. Tangent is opposite the 30-degree angle over its adjacent. 1/2 over square root 3 over 2. 1/2 over square root 3 over 2 from the triangle, opposite over adjacent. The 2's are both denominators, so they cancel, and we get 1 over square root 3. So I'll put 1 plus 1 over square root 3 over 1 minus 1 times 1 over square root 3. Now you've got all but 2 points, right? How do you get the last 2 points? Why am I going to take something off for that, even though the answer is right? Yeah, I don't want any radicals in the denominator, and even one more. Yeah, I don't want compound quotients. Quotients of quotients have to go away. Well, do to get rid of these quotients, I'll multiply through by the whatever gets rid of the denominator. Smallest thing to get rid of is to multiply top and bottom by square root 3. So I'll write this as square root 3 times the top over square root 3 times the bottom. See how much algebra you learn in this class and why it was actually important. My algebra students always tell me, why do we need to know this stuff? Because they don't get these. This is a mess to leave it like this, right? You don't want to give this to your boss at whatever, Lockheed or something, right? Lockheed Martin. So square root 3 times 1 is square root 3. Square root 3 times its reciprocal is 1. Square root 3 times 1. Square root 3 times minus 1 over square root 3 minus 1. Now we have that. And we're still, so I got rid of the compound quotients. And you're right, we got to get rid of the radicals of the denominator too. So how do I get rid of that denominator? I can't just multiply top and bottom by square root 3 to get rid of that. It'll multiply the 1 and put another square root 3 in. So I multiply by remember? A plus b square root c, I multiply by a minus b square root c. So minus by plus. So I multiply top and bottom by the conjugate of the denominator. I'll call this square root 3 plus 1. I'll multiply that top and bottom. All right? If I multiply the denominator by its conjugate, all the roots will fall out. And then not so in the numerator, but that's all right. So in the top, if I multiply this out, square root 3 times square root 3 is 3. That's first. Outside of square root 3, inside of square root 3, there's 2 of those. And 1 times 1 is 1. So I get this on the top by FOIL. multiply it out, every possible pair of these. At the bottom though, square root of 3 times square root of 3 is 3. Plus square root of 3, the outside minus square root of 3 from the inside, minus 1 from the last, and these always cancel if you multiply, right? So you get 3 minus 1 is 2 on the bottom. I can write this as 3 plus 1 is 4, plus 2 square root 3, all over 2. There we go. That's a lot simpler than that, isn't it? And there's still a point off. Maybe I should take off 3 if you only get to here. 3 algebra steps. What do I do with that? Yeah, I want to reduce it. Can I cancel the 2's? No. I can cancel factors. I have to factor a 2 out of the whole top and 2 out of the whole bottom, right? So right, the top is a product 2 times something. Well, 2 times 2 and 2 times square root of 3, right? This times this is 4, this times this is 2 square root of 3. And the bottom I can think of as 2 times 1. Now I can cancel a factor, something that multiplies the whole top, a factor of the top with a factor of the bottom, something that multiplies. The whole answer was just 2 plus square root of 3. No wonder I'm taking off points back here for this answer, right? Give this to your boss, not this one, right? That's why we want to do that.
The answer in the back says it's -2 minus.
Oh, yeah, I do that all the time. I take this minus out trying to avoid problems. When I ran it over here, I dropped my minus. Yep. From here to here. Sorry about that. This is why you check your answers. I keep saying check your answers. High scoring students almost always do that. Sometimes still higher than I do. Firstly, pass and won't check my answers till I actually read them. So it's a minus in front of the whole thing. I just dropped it right here. Yeah, thank you. And now minus this gives -2 minus square root of 3. There's another way to do that. That's with the half angle identity. Rather than do it on this one, I'm going to do it on the next one. I'll look at 2b here. Find the exact value of cosine 7 pi over 8. How do I know I can do this one exactly? Actually, not a multiple of 15 degrees, right? 15 degrees is pi over 12. This is not a multiple of pi over 12. So what do I do if it's not a multiple of 15 degrees, pi over 12? But I'm told I can do it exactly. The only other tool we have, this is where it's nice to have your cookbook. The only other tool we have is the half angle. Not a special angle, we can try throwing the sum of difference identities, get trig function of any multiple of 15 degrees, or we can do the half angle identity, get trig function of half of any angle we already knew. 7 pi over 8 is 1/2 of the special angle 7 pi over 4, right? You multiply these, top times top over bottom times bottom, you get 7 pi over 8. If it's half of the special angle, I can do it with the half angle formula. So this one, I don't have a choice. The other one, I could have done either with the half angle formula because it's half of the special, or the sum or difference identity. I prefer the sum or difference identity on that, but you can use whichever one you want. This one, I have to use the half angle identity. Suppose I call this alpha. Cosine of 1/2 alpha is what by the half angle identity? This one you have to memorize too. These sum and difference identities, the double angle identities, and the half angle identities are the new ones that we have since all the group of old ones from the previous. You have to memorize all those, plus still remember the Pythagorean identities, the cofunction identities, quotient and reciprocal identities. What I'll do with that, if it's half an angle, I write it as plus or minus the square root of 1 plus cosine the whole angle, 7 pi over 4, all over 2. That's the half angle identity for cosine. What's the half angle identity if this had been sine? So that's supposed to sine 1/2 this angle. Yeah, you just change the plus to a minus. So those two are really easy to remember as a pair. Cosine, you put one plus, sine, you put one minus. It's that close to being the same thing. And then is it plus or minus? Here's a mistake lots of people make on the test. Where's 7 pi over 4? Oh, yeah, almost all the way around. 8 pi over 4 would be 2 pi. So this is 2 pi less pi over 4. 7 pi over 4 is 8 pi over 4 minus pi over 4 is a whole rotation, 2 pi minus pi over 4. So I go all the way around like this, less a 45-degree angle. This one, and it's 7 pi over 4. Now I can figure out what the cosine of 7 pi over 4 is, right? I drop this perpendicular. I notice the reference angle of the triangle is pi over 4. So this side must be square root 2 over 2. And this side must be square root 2 over 2. And this must be 1, the triangle I memorized again. You'll really blow it if you don't have those two triangles memorized. You have to know these on this test. So that means the cosine and sine are the coordinates here. The cosine is plus square root 2 over 2, and the sine is minus square root 2 over 2. Remember, that's cosine first and then sine. So the cosine of 7 pi over 4 is square root 2 over 2. And again, where's the plus or minus? I might say to myself, well, wait a minute, cosine is plus. It's not plus, it's actually minus. Why is that? This is why I said it's a mistake a lot of students make. They say, oh, it's in the fourth quadrant, cosine is positive, but this is not the angle we're interested in 7 pi over 4. You have to go back to the original function. 7 pi over 8 is actually in the second quadrant. It's half of this angle, remember? So here's 7 pi over 8. With pi over 8 makes a straight angle. With pi over 8 short of a straight angle, it must be in the second quadrant. In the second quadrant, you drop the perpendicular cosine, the x-coordinate is negative. So this is going to be negative here because it's in quadrant 2, the angle is. You go by this angle, not this one, because you're trying to evaluate this cosine, right? So the cosine has to be negative. Is this negative or positive here? Man, it's positive by definition. The radical sign means the non-negative number that has a square. So you get like square root of 4 is 2, not negative 2. If you put the two numbers whose square is 4, you put plus or minus 4. We call this one with the radical the principal square root. 2 numbers that squared give 4, 2 and minus 2. So this is actually a positive number as written, but we want a negative number, we have to put a minus in front. So that's for quadrant 2 for the original angle, not this one. There it is. There's an exact answer, and that's 2 or 3 points off too, because of algebra, right? How can I reduce that? Got compound quotient again is the problem, right? So I multiply top and bottom by 2 to get rid of the denominator 2. All right, that is minus square root twice the top over twice the bottom. All right, that gets rid of this denominator. On the top, I've got 2 times 1 is 2. 2 times square root 2 over 2 is square root 2. And it's all over 4. I have one more step I want to make, right? Square root of the quotient of positive numbers is the quotient of the square root. So I'll write it like this, 2 plus square root 2, square rooted, all over square root 4. Right? Minus in front. Gives me minus square root 2 plus square root 2 all over 2. Don't leave that as square root 4, put it as 2. There's the answer you want. Now I should make one more mention. This one may reduce. The square root of a sum of a plus b square root c sometimes reduces. Let's not do it. It takes a long time. It's complicated algebra. Let's just leave our answers with square roots of square roots, all right? It's not so complicated, but it is complicated to by this token, what happens sometimes in that first problem, we got -2 minus square root 3. If you use the half angle identity, you might get an answer that looks different by the half angle identity because it has a square root involving a square root, but they're actually equal. Try running the decimal on the calculator, you see they're equal, but sometimes formulas being different, you get a different looking answer, and it's hard to reduce it and see they're the same. It's easier just to check on the calculator. All right, but if on the practice test you're finding on 2A, yeah, I got a different answer in the end. It's probably used a half angle formula, and the answer looks different, but actually, if you did the decimal, it's the same as the one. It does work. Okay, so there's some good problems. See how many of these I can get done. I've got these practice problems. I think there's a pretty good set for without being too complicated and long, hitting a lot of the idiosyncrasies of things that go on in these calculations. Here's number 3. Use a half angle identity. To find exactly the tangent of x over 2 if cosine of x is 5/13 and the sine of x is negative. On this one, what I'm trying to get you to do is sort of figure out what kind of problems can I do with all these tools I've got now, right? You don't just want the tools, you want to have some practice working them to see, have a feel for it. Sometimes memorization isn't enough. And this one, I could have given you another problem with it because I might have asked you this instead. Use the double angle identity. Find exactly the value of tangent 2x. So I only gave you one of the two. I said I tried to get some of these odd things that come up. Well, I don't hit all of them. I'll hit related ones and expect you to figure out the others. The idea is this: if I know a trig function and from this one and this one together a quadrant, anytime I know a trig function in a quadrant, I can find all 6 trig functions of x. So keep that in mind when you do the test and the practice test too. Once I have one trig function and can figure out a quadrant by hook or by crook, I can find all trig functions of x from this. That's an important principle, right? If I know cosine, how do I immediately find sine, for instance? Pythagorean identity is a good way, right? Sine is plus or minus square root 1 minus cosine squared. Also know the quadrant, then that determines the sine plus or minus. So the Pythagorean identity, once I know sine, I know cosine. Once I know tangent, I know secant. Once I know cosecant, I know cotangent. They come in pairs in the Pythagorean identities. And those Pythagorean identities, once you know one trig function, you know a second. So from cosine, I use the Pythagorean identity. I'll put it down here. Sine x plus or minus square root 1 minus cosine squared. This is the Pythagorean identity solved for sine. Does that look like it? I said these come up so often you want to memorize it. The Pythagorean identity is sine squared plus cosine squared equals 1. And it is true we don't want to memorize more identities than we have, but this comes up so often that you need to solve this in sine or cosine that it behooves you to memorize this. If I subtract 1, I've got sine squared equals 1 minus cosine squared. We use this a lot. We'll see this later today here. And then the sine, if the square of the sine is this, then the sine must be plus or minus the square root of this. Just like if x squared equals 4, x is plus or minus the square root of 4 is plus or minus 2, right? Similarly here, if sine squared is this, then sine is plus or minus the square root of this. And so we call this the Pythagorean identity solved for sine because we just did that, right? So I'll use this. Once I know cosine, I meet in a quadrant or whether sine is positive or negative, I immediately know sine is this plus or minus the square root of 1 minus 5/13 squared. And this is a cooked problem. Remember I told you about Pythagorean triples? What were those? Just for your education, if you're a math major or studying to be a high school teacher or something, Pythagorean triple is numbers A, B, and C is a triple such that A squared plus B squared equals C squared. It makes whole numbers on a right triangle. So whole numbers A, B, and C that fit in a right triangle, A squared plus B squared equals C squared is called a Pythagorean triple. So the famous one is 3 squared plus 4 squared equals 5 squared. Use a 3, 4, 5 in the triangle, right? This comes out of a Pythagorean triple, actually, 5, 12, 13. Sometimes I try and give those on tests to avoid nasty fractions, and that's what I've done here. So you might guess there's going to be a 12 come out of this. So it's plus or minus, and then I use sine of x is less than 0. That tells me minus, right? So once I know cosine in a quadrant or for a quadrant because sine is negative, I know the sign immediately. It's minus the square root, and in order to evaluate this, see 5/13 is 25 over 169, right? This is where it helps to know your squares. And then I need to put 1 with a common denominator, so I'll write it as 169 over 169. Once I have a common denominator, I subtract the numerators to get 144 over the common denominator, right? Then I recognize this is a square and this is a square. This is where the Pythagorean triple comes in. I get minus 12/13. I could have got a nasty square root if I had chosen a Pythagorean triple of 5, 12, 13. 5 squared plus 12 squared equals 13 squared. Trigonometry. So I know the sine, I know the cosine, I can get all the others I need, right? Like now tangent is just sine over cosine, this over this. Cotangent is this over this, secant is 1 over this, just turn it upside down. Cosecant, you turn this one upside down. See how you get all 6 once you know a trig function and quadrant? Use the Pythagorean identity to find one more, then use the reciprocal and quotient identity to find the other 4. This is the most important case, given cosine, find sine, or given sine, find cosine. Now the trick on these where I say given these and find tangent of a double angle, or in this case, tangent of a half angle. X over 2 is a half angle problem, right? It's tangent of 1/2 times x. There's a formula for that. You just have to memorize it. The half angle formula is, remember this one? Plus or minus the square root. And you take the half angle formula for sine, which is 1 minus cosine x over 2, and divide it by the cosine formula, 1 plus cosine x over 2. The 2's cancel. So if you take the half angle formula for sine and cosine and divide them, the 2's cancel. So memorize this one, but the way I used to remember it is it's just the quotient of the sine and cosine half angle formula. All right, so I've got this, and now, boy, I didn't even need sine, did I? But in general, I might need it. In fact, I could have just done it here, couldn't I? And then, is it plus or minus? This is tricky here. Is it plus or minus? Here's what you do. You say cosine x is positive. Sine x is negative. Where is that the case? Cosine is the x coordinate. Sine is the y coordinate. We're down in quadrant 4. So x, wherever it is in quadrant 4. 3 pi, well, we put less than actually in the quadrant. Between 3 pi over 4 pi over 2 and 2 pi, right? But what we're trying to find is not tangent of x, but tangent of x over 2. So we'll divide this through by 2. And we'll say 3 pi over 4 less than x over 2 is less than pi. The angle we're trying to find the tangent of is actually in the second quadrant, right, is between 3/4 pi and pi. And here's our x somewhere over here between there and pi, a straight angle. 2. So this is gonna be in quadrant 2. We don't know what it is. But because x is in quadrant 4 for the cosine to be positive, the sine to be negative, that forces x over 2 to be in quadrant 2. And now, in quadrant 2, tangent is negative, so we choose the minus. It's that tricky. Now cosine was 5/13. So we get minus the square root of 1 minus 5/13 over 1 plus 5/13. There's the exact answer. On all these, where I give you a trig function in a quadrant or something, you can figure the quadrant. And ask you for a half angle or a trig function, a half angle or a double angle. What you do is just write the half angle or double angle formula and give you part credit. Like here's the half angle formula. Just do this, you get part credit, right? Right? If you see a half angle, write the half angle formula. Then use these to find the trig functions you need. Here it turned out I didn't need it, but in general you might need it. It's not given. And plug them in, and then you can evaluate the half angle. Or double angle, if I give you that one. It's the same thing, just with the double angle formula. Let's see if I got enough. Once again, compound quotient, so this is minus the square root, and I'll multiply the top by 13 to get rid of the denominator. And the bottom by 13. But don't change the quotient. That gets rid of both denominators. Let's see. 13 times 1 minus 13 times minus 5, 13 is minus 5 over 13 plus 5. This comes out to be minus the square root of 8/18, which reduces, since they have a common factor of 2, minus square root of 4/9. Oh, 4/9 squares. The answer is minus 2/3. Good thing I used the Pythagorean triple. So there's the tangent of x over 2, given just the cosine of x, and the sine is negative. Write the half angle formula, figure whatever trig functions you need from the one you have, and then plug them in. Trig function of half an angle. Okay, hopefully that looks all right. I'm gonna skip over number 5 if nobody wants it. Anyone see number 5? It's taking a product, a sum. We did a sum to product. Now I'm giving you the formula, asking you to product of sum. Again, it's just plug in the identity. Maybe it's worth seeing. I don't know.
I would like to see it, just.
Okay. 5 then?
Yeah.
Says, rewrite. Let's see. No, it's not. Yeah. Rewrite the product as a sum or difference. Oh, it's a difference. Rewrite as a difference of trig functions. 20 cosine 3 theta sine 4 theta using the product of sum formula, sine x cosine y equals 1/2 sine x plus y minus sine x minus y. this being a product of sum formula and a product of difference formula, I give you the formula. Well, you say, how can I make this look like this? Well, what I can do is factor the 20 out and say, well, this is 20 times, and I'll just multiply these two functions in the other order. All right, sine 4 theta, cosine 3 theta. Multiply in the other orders. Right? Let's put parentheses to break these out, but don't have. But now sine of x, if I let x be 4 theta, times cosine of y, if I let y be 3 theta, just substitution. By this half angle identity is equal to 1/2 sine x plus y, so it's sine x plus y minus sine x minus y, where x is 4 theta and y is 3 theta. So sine x plus y, sine x minus y, where x is 4 theta, y is 3 theta. And now it simplifies. 20 times a half is 10. This is sine of 4 theta plus 3 theta is 7 theta. And 4 theta minus 3 theta is theta. Maybe to strictly follow the prescription, I should call it 10 sine 7 theta, 10 sine theta. I'll take either of these answers. You can write this one or you can write this one. I wrote it as a difference of sine functions. It's just a matter of rearranging it by algebra into the form that you see here on the left, and then saying, oh, this must be x, this must be y. Let's look at 6b. Suppose I wanted to solve a trig equation. I'm going to give you some trig equations on here. And I said solve exactly for all possible theta. All possible theta means what? Yeah, I have to include a plus 2k pi when I evaluate things. So I get not just in one rotation, but all possible angles. And the problem is secant 2 theta equals minus square root 2. What did we say was the method for solving this one, where it's trig function equal to numbers?
Circle.
Yeah, use a circle to set theta, or since I've already used theta, I'll call it alpha, to be the angle that's here, and apply the unit circle. So I've got secant alpha equals minus square root 2. That's what we call method 1. You have trig function equal to number, just write your favorite letter for the angle and apply the unit circle. Even if it's not a special angle, you can still get the exact solution in terms of inverse trig functions, right? So I'm going to solve secant alpha equals minus square root 2 on the unit circle. Uh-oh, how do I do that? Secant isn't the x or y coordinate.
Over the
Yeah, awesome. If you got secant or cosecant, rewrite it with reciprocals. If these two are equal, their reciprocals are equal. Cosine, the reciprocal to the left, is minus 1 over square root 2, the reciprocal to the right. There it is. Moreover, if I'm clever, I might recognize 1 over square root 2 is also known as square root 2 over 2 by multiplying top and bottom by square root 2. And that looks like it came from a special angle. So I'm solving cosine alpha, which is the x coordinate of the unit circle, equal minus square root 2 over 2. Now that's about minus 0.7 or so, so it's about here. It doesn't have to be drawn real accurately. X equals minus square root 2 over 2. The only points on the unit circle that have that x coordinate, there's going to be 2 of them. Since this is between 0 and -1, it's going to cut the circle in 2 places. I'm going to have only this terminal ray and this terminal ray possible. That's it. Right? Only 2 points on the unit circle with that x coordinate. There's only 2 possible terminal rays through them. Now, what are those angles? the x coordinate is minus square root of 2 over 2 here. This length here must be plus square root of 2 over 2, right? It's a unit circle. Ah, square root of 2 over 2 and 1. This must be a 45, 45, 90 triangle. That's pi over 4. And by symmetry, this one is also pi over 4. It also has a square root of 2 over 2. Now I can figure those angles nicely. Alpha, the angle I'm looking for, is pi back up pi over 4. Or pi go forward pi over 4. And I simplify these to 3 pi over 4, right? This is 4 pi over 4 minus pi over 4 is 3/4. That 1 minus a quarter pi is 3/4 pi. 1 pi plus a quarter pi is 5/4 pi. So those are all the angles alpha. Here's the two I drew within one rotation, but if I want all angles alpha, I take these plus 2k pi. There's all angles alpha. K can be any integer, a number with nothing after the decimal.
And you only do that when it says exactly all possible angles. Like how do you know when you don't have to do the plus 2k pi?
You don't have to if I ask you for angles between 0 and 2 pi, and the angle is just theta or just x, whatever is a single variable. But whenever it's a multiple like this, you have to find all angles, and then if it says restrict to 0 to 2 pi, you have to find all angles and then reduce it to those between.
Okay, I understand.
Yeah, okay. So just if it's restricted to 0 to 2 pi and you have just a letter here like alpha, then you don't have to put plus 2k pi.
So like on part A, when it just says tan theta, then we don't have to do the plus 2k pi?
You do because it's asked for all possible angles. So if you have just an angle and I restrict you to 0 to 2 pi, then you don't need the plus 2k pi. Otherwise, put it in. And I'll mention this here. These are all angles alpha, but alpha is equal to 2 theta. All right. So now I divide this by 2 to get theta. All angles theta are theta equals 1/2 these values. 3 pi over 8 divides that angle by 2. 2k pi divided by 2 is k pi. 5 pi over 4 divided by 2 is 5 pi over 8. You have to divide the whole side by 2. Plus k pi is this divided by 2. There's all angles theta. Now, suppose I said I want to solve this on the interval 0 to 2 pi. What would I do? I still need to do this. Even though it's a 0 to 2 pi, I still need to do this, and then I'll throw out the ones that aren't between 0 and 2 pi. Because what happens is this only gives me the angles alpha between 0 and 2 pi. And since 2 theta is equal to alpha, there might be some other ones here where theta is between 0 and 2 pi, even though alpha wasn't. In other words, if alpha is between 0 and 2 pi, theta can go between 0 and 4 pi. I'm sorry. If theta can go between 0 and 2 pi, then alpha is allowed to go between 0 and 4 pi. And rather than figure it out, I just usually say find all the angles and throw out the ones that aren't correct. Here I said all angles theta, you just stop right here. But if I say all angles between 0 and 2 pi, you still do this, and then you throw out the ones that are small. And the one time you don't have to do that, if I just said like trig function of theta, 0 to 2 pi, then you just find these angles and you're done. Just if you have both these things, a single letter, interval 0 to 2 pi. Otherwise, do this plus 2k pi and restrict it if you need. All right, so there's all angles theta. There's an infinite set of them. And I'll just remind you, you don't have to write this because k equals an integer is assumed unless you say otherwise, but k is any integer number from this list. Getting there. These are going to be harder problems, aren't they? But they're good ones. They really teach you the ins and outs of these things. You'll be successful in all your science classes that use this. Maybe we should do, well, no, let's do this one. Let's do 7. Tell me if I'm skipping 6A here. If anybody wants to see it, we can do it. Suppose I do 7A. And I'll say sine 3 theta, or 3 sine theta, excuse me, plus 5 equals 0. Suppose I want to solve this one. What do I do for that?
You subtract b.
Yeah, this is what we call method 2. It's not listed that way in the book or any book I know of. I'm just trying to categorize the usual steps here by calling a method 1. When it's a times trig function plus b equals 0, or it can be put into that form, then you subtract b and divide by a and get sine theta equals minus 5/3, exactly. Now what are the solutions? You can quit right here. The solutions are, that's what you said, nothing. That's very good. Yeah, the reason is if this number is bigger than 1 or less than -1, is in this case, there's no solution. Sine is always a number between plus and -1, and you can stop right there. There's no solution. This symbol means the empty set. Right? No solution. How about that? That one wasn't so bad. How about 7B though? Well, I asked you to solve 2 secant squared theta minus 2 secant theta minus 3 equals 0 for 0 less than or equal to theta less than 2 pi, angles within 1 rotation and round 2 decimal places. What is that round to 2 decimal places?
Use your calculator.
Yeah, you're gonna need the calculator, and the reason you're not gonna get all special angles. At least some of the angles will be non-special. So you have to get a rounded result. All right, can't leave it in terms of pi and square roots and things. Now, what method do I use for this? What I call method 4, you don't have 3, you don't have to remember the number. If you have a quadratic equation, a times trig function squared plus b times trig function plus c equals 0. Make sure you get 0 on the right. You let u equal the trig function you see to get a quadratic equation, right? So I get 2u squared minus 2u plus 3 equals 0 is the corresponding quadratic equation in u. Then there's 2 methods to attack this, the factoring or the quadratic formula. Maybe you remember it'll factor nicely with whole numbers if b squared minus 4ac is a square. We can calculate that if we want. I think I'll just go to the quadratic formula. Quadratic formula always works for these, all right? The reason I do that is I think b squared minus 4ac is not a square. We can calculate it. B squared minus 4 times a times c is 4 plus 24 is 28. That's not a square. Right, square root of 1, 0, 1, 5, 0, 1, 4, 9, 16, 25, right? So I'm going to have to use the quadratic formula. If this isn't a square factoring, I'm not going to be able to guess what goes in. But this is positive, means there's 2 solutions, right? Greater than 0, I'm going to get 2 solutions. It's over. This is your discriminant, they call it in algebra, b squared minus 4ac. The quadratic formula says, right, I'll write it down to remind you, you have to know this for the test. I'm going to make you use it at least once. Minus b plus or minus square root of b squared minus 4ac all over 2a. Solves this every time, including if it has no solution, it'll tell you that, right? Minus b is plus 2, plus or minus square root. Oh, wait a minute, I already did b squared minus 4ac over here, right? 28. So if you check it ahead of time, you can just put it in. All over 2a, 2 times 2. Gives me Well, I don't want to write 2 plus or minus square root 28 over 4. Why not?
Cause you're just gonna like reduce.
Yeah, it reduces. This is easier if I think at the top as 2 plus, now square root 28 is also square root 4 times 7, and the square root of the product of positive numbers is the product of the square roots. This is 2 square root 7. If I write it that way, I recognize I can cancel something, right? This is twice 1 plus square root 7 on the top over like 2 on the bottom, and the 2's cancel. Right? Factor of the top, cancel a factor with a factor of the bottom. Treat a factor first. So this whole thing is actually just 1 plus square root 7 over 2. Easier. This is one of the harder problems on a practice test, by the way. We need to do this one today. Otherwise, you'll all be over one at a time. Asking me at my office there. I used to teach a differential equations class, and all my students would come over and same problem.
Wait, how do you know on this one? Why did you just drop the negative, like, for the negative plus or
Well,
minus?
plus or minus, that's because I forgot to write it. Infinity?
So it is
Yeah.
1 plus.
Yeah,
or
it
minus
is 1
1.
plus or minus. Yeah, there's 2 solutions. All right, so u can be either of those things, but u was secant theta, so what we have now is secant theta equals 1 plus or minus the square root of 7 over 2. This original equation is equivalent to this one. I'll put double arrows to point that out. This is the same solution set as that had. 2 solutions, 1 for the plus and 1 for the minus. Now, this one is hard to solve on the unit circle, but we do say at this point that we can go back to method 1. Well, actually, let's write it as both these. Let's write it. Secant theta can be 1 plus square root 7 over 2, or secant theta can be 1 minus square root 7 over 2. Now it's trig function equal to number, trig function equal to number, it's back to method 1. Whenever it's trig function equal to number, you solve it in the unit circle, right? However, when it's secant, what you really want to do is write the reciprocal, right? So I'll write cosine theta equal, the reciprocal of this is the reciprocal of this, just turn it upside down, 2 over 1 plus square root 7. Or cosine theta might be 2 over 1 minus square root 7. This is where I like the problem I gave you. It really pulls out all the stops, doesn't it? I think. Well, I solved this one on the unit circle, and I solved this one on the unit circle. And there's a little help here. You can figure it out actually without the unit circle, but what is this number about? If I calculate this on my calculator, that 2 divided by, make sure on this long, when you do this on the calculator, put parentheses in here. Your calculator doesn't do a long bar, otherwise it will do the division and then the subtraction. Keep 2 over 1 minus square root 7 if you don't put your parentheses. Calculators that don't put a long bar. So I'll take 2 divided by parenthesis 1 minus square root 7. And I get minus 1.21. So what's the solution set to this one? Oh, 1.22, I guess it rounds to. Yeah, there's no solution, right? Cosine, it has to be a number between plus and minus 1. This one's less than minus 1. So there's no solution. Graphically, if you drew the unit circle, here's the unit circle going out to minus 1. We want cosine, the x-coordinate to be minus 1.22, so here it is. X equals minus 1.22. It doesn't intersect at all. There's no solution, right? But once you see it's less than -1 or bigger than 1, you don't even have to draw the picture. So the solutions here are none. How about solutions here? This one will have solutions because this number is between 0 and 1, right? This number here, whatever it is bigger than 2, right? Like square root 7 is bigger than 1, so the sum is bigger than 2, and so the denominator is bigger than the numerator. This is This is less than one, right? The bottom is bigger than the top, it's less than one, and it's positive. So it's over here. So this is greater than 2 positive, and the top is positive. The quotient is a positive number between 0 and 1. I can draw a line anywhere. It won't matter if it's not real accurate. Suppose this is x equals 2 over 1 plus square root 7. Wherever it is, it's over with x positive, but less than 1. And so I'll get 2 intersection points in the unit circle here and here. Hence 2 terminal rays, and that's it. Only 2 possible terminal rays. So what's the solution to this one? Cosine is equal to some number between -1. Well, there's always one solution. What's one solution always if cosine is a number between plus and -1?
Arc cosine.
Awesome, yeah, arc cosine. Right? Arc cosine of that number is always one solution. Okay, is it this angle or this angle or what is it? Gave it away. Couldn't resist. The arc cosine is the one of these two that's between 0 and pi, right? That's why you have to know the range of sine, arc cosine. Arc sine is always between -pi/2 and pi/2, so is arc tangent without the endpoints. Arc cosine is between 0 and pi, these two quadrants. So you throw out this one is the arc cosine. So that's one exact solution. How about that? This over a little. What's the other one? What I've got on here, elected to write it on the beginning, but I think it said 0 to 2 pi, didn't it? This is 70. Yeah. So right on here, this is 4, 0 less than or equal to theta less than 2 pi was in the instructions. And then rounded. Oh, I did write it. I'm sorry. There it is. Put it up top. So I don't want to do this angle. This would be minus the arc cosine, right? By symmetry. If this is arc cosine and this triangle and this one are congruent, then this must be minus arc cosine. But that's wrong because it's negative. So instead, I have to take this one all the way around here. And what's that? Well, by symmetry, this is also the arc cosine if I go the same direction. Right? Going this way would have been minus the arc cosine. And so I have 2 pi rotation less the arc cosine. There it is. This one, 2 pi minus arc cosine 2 over 1 plus square root 7. This one has no solutions. So what we found out is that this one has exactly 2 solutions. And they are theta equals arc cosine 2 over 1 plus root 7, and theta equals 2 pi minus that arc cosine. There we go.
It says rounded 2 decimals.
Yeah, that's what I was getting to. Your woes are not done because actually rounding these to 2 decimal places is not trivial. It's not hard. But you have to be able to use your calculators on these, right? If you're working for a surveying company, they don't want this. They want, how many degrees is that, right? So I can measure it on my, whatever. If you're doing a telescope, telescopes do use these trig functions a lot, right? The way you find stars, you take a azimuth and a right ascension or something like that, and you'll measure these things in degrees usually, and minutes and seconds of arc. And so you use a lot of trigonometry actually in calculating things in the sky. Also on maps, you ever seen maps? They've got latitudes and longitudes, do the same kind of calculations. Sometimes they use spherical trigonometry, which is very similar to what we do plane trigonometry. All right, so here's the 2 answers exactly. If I ask for exact answers, you leave them just like this. But since I asked you to round them, here's how you can calculate this one. To get the inverse cosine or arc cosine, you put second cosine because up above this function is its inverse. Right? Make sure you're on radians mode because I asked for theta between 0 and 2 pi. I don't want to see the degrees thing. So check first radians mode, then push these second arc cosine, it will put in a parenthesis automatically and put arc cosine parentheses. So this is the display. These are the keys up here. Now I want 2 divided by, some of your calculators will put a long bar, but if you like my old clunker here, you'll need to put in a parenthesis here because, again, it will do divisions before additions, right? It'll make this, if you put 2 divided by 1 plus square root 7, it will do it this way, unless you put parentheses here. So this long bar means there's implied parentheses here. If your calculator doesn't draw the long bar, you have to put these parentheses in. So I'm going to say, put in a parenthesis here on this calculator, at least. I'll just put it in here. I think it's a clunker. Arc cosine 2 divided by parenthesis 1 plus, and we get square root, it's the inverse of the square, so you put second x squared, because over it is its inverse, square root of x, but under the square. Or maybe it's a square root. And then I'll push the 7. The calculator automatically puts a parenthesis here. If your calculator doesn't put 2 parentheses, then you need to close the parenthesis on the square root. And it'll put arc cosine 2 divided by, for the divide, it'll put a slash, parenthesis 1 plus square root 7. This is a display. Now, when you push this one, it closes it, or the calculator does it anyway. And then you can close it again. The TI-84 will automatically close all these, but I recommend going ahead and closing them here, just to make sure. If you accidentally put an extra, put one parenthesis too few over here, this will catch it because you have to. Sometimes you catch an error. It should look like this. The thing to do is look at the display. It should say arc cosine 2 divided by parentheses 1 plus square root 7. Actually, we need to close the parentheses on the square root. So let's see. X squared closed. Okay, close the parentheses around the 7. Close the parentheses for the bottom, and then close the parentheses for the arc cosine. So actually, there's one here that needs to go here because you inserted it. Close the square root, close the arc cosine if it doesn't already. And so you should have 3 parentheses here. So it'll look like this on the display. Square root of 7. Close this parenthesis, close this parenthesis. All right, so just make sure it looks like that. Is the trick. Inverse cosine 2 divided by parenthesis 1 plus square. Parentheses at the end. Yeah, 0.9901. Blah, blah, blah. Round the 2 decimal places means take 2 digits after the decimal point and approximate this by 0.99. So there's one answer. What's the other one? The other one is easier. So this is the first one. The second solution is easier because it's just 2 pi minus the first one. Here's what you can put on your calculator is push 2 times second caret gives you pi. Second caret gives you pi. So this is 2 pi appears on display. 2 half this pi probably. And then minus. So these are the keys. This is the display again. And if you push second and the little minus key on the TI-84, it might be different on your calculator, the Casio or Sharp or something. The ANS is above here. You push second minus it, it brings back the old answer. It'll put ANS on the screen. It'll take 2 pi minus the one you just had. So let's try that. 2 times pi minus, my last answer is 5.29. All right, so we'll carry all the digits. You don't have to worry about. I think I'm trying to put it in. Those are our 2 answers then, 0.99 and 5.2. Oh, and one thing you notice on there too, I didn't go back and put plus 2k pi because I was asked for just the one angle. It's not a double angle or anything. The letter is the angle and it's between 0 and 2 pi. Then I don't have to go back and put plus 2k pi anywhere. That will give me the solutions right there. All right. Suppose I gave you AT. I said solve this trig equation. Sine squared theta minus cosine squared theta is minus a half. I wanted to do this one to show you one more method. What should I do with this one? All right, remember your prescription. The trig function equal a number, you just use the unit circle. If it's a trig function plus b equal a number, all right, let the trig function equal minus b over 2a. If it's quadratic in a trig function, you write the quadratic equation, like u equal the trig function. But if it's got more than one trig function, two different things we did. We could use the identity to write it with just one trig function, or we could try and factor using the two trig functions and 0 on the right. Each factor having one trig function. This one, I notice whenever I see in one of these things a square of a trig function, I think immediately, what if I put in the Pythagorean identity? Cosine squared is 1 minus sine squared by the Pythagorean identity. Then I'd only have one trig function. There's the trick. Make an identity. This is method 4. We call it apply an identity to get rid of a trig function. Now it's sine squared minus 1 minus sine squared. Make sure you put this whole thing in parentheses. You're subtracting the whole thing, right? Equals negative a half. It's equivalently sine squared minus a minus sine squared is 2 sine squared. Minus 1 equals minus a half. Add 1 to each side, and you've got 2 sine squared equals plus a half. And this is actually this is a trig function squared plus b trig function plus c equals 0. You could use method 3. But one reason I wanted to do this one is that sometimes there's a shortcut. If I can write this as a square equal a number, which I can, right? This is equivalently sine squared equals 1/4 by dividing both sides by 2. I don't need the quadratic formula, even though that'll work, or factoring, even though that'll work. They both work, but it's easier when you see trig function squared equals a number just to say, oh, sine squared equals a quarter. I know immediately that sine is plus or minus the square root of a quarter. That is plus or minus a half. Square of a half is a quarter. That's easier. So sometimes in method 3, you kind of see a square equal number, just do that. Don't have to. Now I have 2 unit circles, which method 1 applies. Sine theta equals a half, or sine theta equals minus a half. I think I said solve this on 0 to 2 pi, didn't I? Yeah. So, and on the test, what I'll do is I'll give you all ratings, all right? 0 less than or equal to. That way you won't have to keep putting it back and forth between degrees. All right. I always hate that. I live in the wrong mode and miss every problem. I said that before. I just hate that. Sine theta equals a half or minus a half. Like the person who's playing the piano, they start on the wrong keys, and so move their hands to the wrong spot. It's terrible, terrible music. All right. Now method 1 means solve it on the unit circle. Sine theta is the y coordinate. All right. So on this one, I look for y coordinate a half, halfway up to the top of the circle. And this one, I look for y coordinate equal minus a half, halfway from the middle to the bottom of the circle. Observe that I've got 2 terminal rays up here. All right. And 2 terminal rays down here. Now, once again, since it's just theta, not a multiple of theta, and between 0 and 2 pi, I don't have to put the plus 2k pi, just solve these 2 cases. I'm done. So I'll drop the perpendicular here and recognize what kind of triangle is that.
69.
Yeah, there's a 1 here and this is 1/2 unit up, so it's 30, 60, 90. This must be pi over 6, yeah. By symmetry, this is pi over 6, and I see immediately my angles are pi over 6. If I back up, pi over 6 is 5 pi over 6. Then I've got some here. I drop the perpendicular, it goes up 1/2 unit from y equals minus 1/2. This is 1, so this is a 30, 60, 90. This must be pi over 6. By symmetry, that one's also pi over 6. I have pi plus pi over 6 is 7 pi over 6. 2 pi back up pi over 6. If I can do this awfully quickly, I'll call it 11 pi over 6. I know I left out a lot of subtractions, but I'm short on time. This, 2 pi minus pi over 6 comes out. There's 4 answers to that one. Okay? Then there's some things in establishing identities. That's kind of tricky too, right? These proofs are hard. So I'll try not to make them too complicated here. Also number 10, let's look at number 10. Let's say right is a single trig function. Suppose I gave you this in A, it's cosine 5x, cosine 3x, minus sine, plus sine 5x, sine 3x, and that 9 is a typo. How does that reduce? The trick on these is to say, what does it look like that I've seen? Yeah, if I say cosine, cosine plus sine, sine, that looks like a difference identity. I remember this one, cosine, cosine plus sine, sine is cosine of alpha plus beta. This is why you have to memorize those. You want to be able to look at this and say, that looks like something I know. So if I call this alpha and this beta, then this is also alpha and beta. And I'll just write, oh, that by the, this is minus though, I'm sorry. This is the difference identity, cosine alpha minus beta is 5x minus 3x. It's just a single function cosine of 2x. How about that? Easy as that. That's what I want to do on these.
What do you do with the 9?
The 9 was a mistake. That's a typo. I'm sorry.
Okay.
Double fingered there. And then finally, suppose I have cosine 2x, sine 2x. How do I reduce that one to a single trig function? What does that look like that I've seen before? Again, it's the duck rule. What does it look like? Sine, sine of 2 alpha is 2 sine alpha cosine alpha. It looks like that one, right? It's not, oh, except it's cosine times sine. I can fix that. What I'll do is I'll rewrite this in the other order, sine 2x cosine 2x to match what I remember in my identity, right? And I need a 2. Well, I'll put it in there, right? If I don't have a 2, I'll put it in and cancel with a half. And now I've got it because this is equal to this. I just multiplied the other order and put times 1. It's half times 2. 2 sine alpha cosine alpha is sine is twice that angle. This is 1/2 sine of, and in here I should put 2 alpha, but alpha is equal to 2x. So I get 1/2 sine of 4x. And I get sine of 2 alpha where alpha is 2x. There it is, single trig function. So it's, you know, what does it look like on those kind of rules? And that looks like I'm out of time. All right. So, boy, we almost got done. 5 more minutes. We could have knocked this thing off. Hopefully, I'll help you get ready. Come see me in my office hours. I'll put this up online if you want to look at the. Look at this again on YouTube. You can't remember something.
12:30, 1:13 tonight.
Yeah, yeah. Everybody online for coming in.